Okay, here we are, lesson number 2, and we're talking about the transmission and the speed of sound. And really, we could actually talk about the transmission and speed of really any type of wave, but we're going to use sound as an example. This is a movie poster from the original movie Alien. It was made in 1979, and it was kind of this science fiction-y horror type movie. And of course, their tagline is "In space, no one can hear you scream," which is actually very appropriate because the tagline is very true. Sound is a type of wave, it's a mechanical wave, and in order for a sound wave to travel, it needs a medium to travel through. It's like water waves. You can't have water waves unless you have a medium for that wave to travel through, which is water. Well, sound is the same thing. Sound is a wave that happens through the air. And the only reason that it happens is that pressure changes in the air spread out in a certain fashion and move around from one place to the next. And so this is a very, very kind of childish example, but here, we have someone talking, and of course this person's vocal cords create pressure fluctuations in the air. And one region of high pressure air, kind of, and those air molecules bounces off of another region of high pressure air, so that this sound wave transfers out and hits this other person's eardrum, which in response vibrates because of the changes in pressure in the air. And this is how sound waves travel. Okay, we have regions of low pressure, and then we would have regions of high pressure. And this is highly exaggerated, but this is in general what happens when a sound wave spreads out. These dense areas of air we call compressions. Okay, and then the less dense areas of air we call rarefactions. And air is kind of a good idea of gives us a good idea about how waves travel. But air is only one example of a medium that can transmit sound, or rather that can transmit a wave. And medium has a very, very large effect on transmission, especially the density of transmission. And so there's a little chart here that lists different materials and different densities and the speed of sound that waves would travel through these different mediums at. So as a general rule, as the density of a medium increases, the speed of the sound wave also increases, but that's not always true. That's not always true. The speed of sound is greatest in solids and smallest in gases, but in general that can change. When you look at, say, the density of iron, which is 7,800, it has a speed of sound of 5,000, and then you look at the density of aluminum, which is 2710, and its speed of sound is a little bit higher. So it's not this isn't a hard and fast rule, but in general, with increasing density, we see increasing speeds of sound. But of course, you can see here that there are some differences, there are certainly some differences. So this rule does not always follow. But what we do notice is that the speed of sound in air roughly is about 331 meters per second. But the speed of sound in something like oak or something like crown glass or something like aluminum is much, much higher and very significantly higher. So we have a little bit of example. The speed of sound in a certain type of hardwood is 4,000 meters per second. So what's the difference in arrival time across an 800 meters? So let's say you've got a huge banquet hall, 8 football fields long. I'm not sure if one of these actually exists, but let's say you do. And you've got a sound that's traveling through the air, and you've got that same sound at the same time someone sends a wave of sound or a vibration that travels through the hardwood floor. So let's say you shout really loud, and at the same time you stomp your foot really, really hard, and that causes a wave to travel through the hardwood floor. What is the difference in arrival time? Well, let's take a look at these things. We know that the velocity of sound in hardwood is 4,000 meters per second. Velocity of sound in the air is about 331 if we look at that chart. We know if we rearrange our formula, which is that velocity is equal to distance over time, for No acceleration, because in general, we're not talking about any acceleration. The sound's not speeding up or slowing down. It's just traveling with a constant velocity, so we're safe to use this equation here. Right? What we can do is we can say, okay, well, the time that it would take across the hardwood would be 800 meters divided by this 4,000 meters per second. So it's going to get there really quick. So it's going to traverse an 800 meter expanse in about 0.2 seconds. So now we can do the same thing, but let's do the time that it's going to take this sound to travel in air. And here we have about 800 meters. Again, the same distance in both cases, but this is divided by 331 meters per second. So a much slower speed, and we get about 2.4 seconds as the travel time. And if we take the difference in arrival time, which is delta t, we get about 2.2 seconds, which is actually a long time if you think about it. 1 steamboat, 2 steamboat, right? Like that's actually quite a substantial amount of time when you're talking about arrival times of different types of waves, okay? So as we move on, not only is the speed of sound dependent on the material that a wave travels through, but it's also dependent on the temperature. And we're going to look specifically at air, because most of the time we are going to talk about sound moving through the air, and so we need to know how the temperature of the air will affect the speed of sound. And we have this nice little formula that's given to us, and sometimes in different textbooks you see different things. In certain textbooks you see 331 plus 0.6 t. In other textbooks you see 332 plus 0.6 t. For the most part, the difference is negligible. I don't know where these differences come from, but different textbooks have different formulas. So this is the one that I chose to put in my notes, 332 plus 0.6 t. V is, of course, the velocity of sound, or the speed of sound in meters per second. It wouldn't be the velocity of sound. It would be more accurately the speed of sound, because we're not really talking about a vector. And T is the temperature in degrees Celsius. Okay, so let's just take a look here. Given a summer temperature, sunny summer day, 20 degrees Celsius, what's the speed of sound? Well, given that and given the formula, we can do a quick substitution and we can determine that the speed of sound on a sunny summer day is 344 meters per second.